I think you're on mute, Jelani.
Yes, thank you. Can you hear me now?
Yep.
Okay, great. Yeah, so hello everybody. Just one logistical thing I want to get out of the way before we start for today. I know that there are several of you who are interested in registering for the course, but couldn't yet because of the enrollment cap. I'm just talking to the department, now about getting permission to have a GSI for the course. There are 86 people in total who seem to be interested in taking the course with an enrollment cap of 25. I'm more than happy to teach as many as possible. It's just if the number gets really big, I would definitely need GSI support for grading. So once I get that confirmed, I'm going to increase the cap. Hopefully it gets confirmed. If it does, then I'll be able to increase the cap. So I'll make that announcement on Piazza when I get more information. In the meantime, just feel free to keep coming to lecture. At the very least, you're allowed to audit if it turns out that I won't be able to take more registered students. But I hope to get that information in the very near future as to whether we're able to get a GSI or not. Okay. Good. So let's continue where we left off. And I hope everybody noticed that the first lecture is online. It's on YouTube. It's linked from the lectures portion of the course website. And you do need to be logged into your berkeley.edu email address on YouTube to be able to watch the video. There are a few of you who are listening to the course from the Simons Institute who might not have a berkeley.edu account. If you're in that situation, just send me an email and I can give you permission to be able to watch the video. Okay, so let's start. So last time we did approximate counting via the Morse counter. And this time we're going to continue with counting, but we're going to look at count distinct. So the input stream is just a sequence of integers, I1, I2, up to, let's say, IM, where each one of these is some integer between 1 to n, and then query how many distinct integers were in the stream. Right. So just to be clear, let's say I have a stream that looks like 1, 1, 5, 1, 3, 7, 4, 4. Then what are the distinct elements here? Well, there's 1, we've already seen 1, there's 5, there's 3, 7, 4. So the answer here would be 5. So okay. Now there are two trivial solutions. Remember, our goal is to minimize memory consumption. So the first trivial solution is to maintain a bit vector of length n, right? So whenever we see if we see integer I in the stream, we just set the ith bit of our bit vector to 1. Otherwise, initially the entire bit vector is set to 0. So that's n bits of memory. And then when it's query time, we can scan over the input and scan over the bit vector and just see how many ones we have. Okay. So this is n bits of memory. And the second trivial solution is just to remember the entire stream. So each input in the stream is a log n bit number. There are m numbers, so m log n bits. And that's remembering the whole stream. Okay. So our question here is whether we can, beat these naive bounds, and we're going to beat them exponentially. Okay, we're going to, instead of using the min of, say, n and m memory, we're going to use something that's more proportional to the logarithm. So, today, I think we're not going to actually see Well, I'll mention some. We're not going to see the optimal algorithm today, but we're going to see algorithms that are pretty good. Okay. Um, so first, I want to say that um, Alone, Matthias, and Segedi showed that um, there is no, you know, low memory algorithm and when I say low memory, I mean like little o of say the min of n and m bits, unless you're both randomized and approximate. So what do I mean by that? Let's say that the true number of distinct elements is, let's say, t. Then what we're going to output is a t tilde. So we want to output t tilde such that the probability that t tilde deviates from the truth by more than a multiplicative 1 plus epsilon error is at most delta. Just like what we saw with the Morse counter, this kind of approximate and randomized and approximate algorithm. Okay. I will show in this course how you prove this, how you prove that there is no low memory algorithm unless you're both approximate and randomized, but that's for later. So now I just want to show you how to actually do it. Okay. And the first kind of non-trivial algorithm that's idealized, and it's idealized in the sense that it's not, there are reasons why you can't actually implement this algorithm as as described in low memory, but if you make certain unrealistic assumptions, then you can. And we'll show later that this work was done in the 80s and basically said if you have random functions that are free to store, which in reality, why would a random function be free to store? But if the hash function, if you had a perfectly random hash function, then we can get a low memory algorithm. Of course, the question then is how do you store this perfectly random hash function? That's another matter, which we'll get to, how to remove that assumption. But if you make the assumption that you have a perfectly random hash function, which I call idealized, then it turns out you can have a low memory algorithm. And this algorithm was due to Flageolet and Martin. Also in the 80s, I think maybe it's 1985 or 82, I don't know, sometime in the first half of the 80s. Okay. And I'll call this algorithm the FM algorithm for Flageolet and Martin. And that's the first thing that I want to describe to you today. And also, before, one other logistical thing I meant to mention, which I forgot, this whole, I guess, Berkeley time of starting 10 minutes into class time traditionally is there to allow people to have time to go from classroom to classroom. But now, since everything is online, I think it's maybe it's just kind of cutting into time that we could be learning cool stuff. So let's have a 5-minute Berkeley time. So from now on, I'm going to start lecturing not at 1:40, but at 1:35. And let's see how that goes. Maybe eventually by the end of the semester, I'll just get rid of it entirely. But now I'm taking baby steps. So Berkeley time is halved from Wednesday onward. Okay, so what's this FM algorithm? So when you initialize at the beginning of the stream, I'm going to allocate one counter x, and I'm going to set that counter to 0. No, not to 0. I'll set it to 1. Okay. And then when there's an update, I see an integer in the stream. And I'll pick a random hash function. h, which maps the integers from 1 to n into the continuous interval from 0 to 1. Okay. So, I mean, what is n? For example, let's say that, you know, I'm a router, I'm monitoring network traffic on some link, and I want to know how many distinct IP addresses, you know, sent traffic on this link. Okay. So then n is something like, you know, let's say it's IPv4, n is 2 to the 32. There are, you know, 2 to the 32 possible IP addresses. And every time I see a packet sent, I look at the source IP, and that, you know, that source IP is an integer I'm seeing in the stream. It's an integer between 0 and 2 to the 32 minus 1, right? And then answering this count distinct question is then telling me the answer to how many distinct IP addresses are sending traffic on this link. Just so you have something, one example to keep in mind. Okay. But this thing gets used all over the place. Update I. Okay, so what is the algorithm to do for update I? It's going to set x to be the min of what it was before and h of I. And then to answer a query for the number of distinct integers I've seen, I'm going to return 1 over x minus 1. Okay. So that's the algorithm. It's pretty simple. Okay. Why is it idealized? I mentioned it. It's because we're assuming access to this hash function, right? In reality, I mean, there are two issues here. One is h, you know, what is h? So you're talking, you know, what is this h here? I mean, to specify h, I have to tell you that h of 1, or h of, let's say, 1 is something, h of 2 is something, h of 3 is something, all the way down to, you know, h of n is something. These are all random numbers. So I need to, you know, I need to store them. There's no simple way to describe h. It's totally random. So I need to store n random numbers. That's, you know, n units of memory, even more than, you know, these random numbers are not just bits, they're real numbers. So let's say n units of memory. There's already a trivial solution that uses n bits of memory, which is the bit vector of length n. So why am I storing n real numbers? That seems to be even worse than storing n bits. Okay, so that seems like a problem. And of course, the other problem is that, as I already said, they're real numbers, they're not bits. My computer can store bits, okay? My computer cannot store real numbers. Now, it can store them rounded to some finite precision. You could analyze this algorithm where you do that. You actually round the range to some finite precision, and you know you'll get something meaningful. But you know that's still more complicated or more memory consumption than a bit vector of length n. Okay, so we're just going to ignore these issues for now, and we're going to assume that we can just store h for free in the sky. Okay, but we will later talk about a non-idealized algorithm that doesn't need to make this assumption. And we're going to touch on, I know someone asked about this last week, we're going to touch on pseudo-randomness, you know, introduce a little bit of the concept of pseudo-randomness and how it can be applied to this situation to actually get a good result. Okay, removing the idealized assumption. But for now, let's just pretend that we have this h. Okay. So, you know, why does what we're doing make any sense? Like, where is this coming from? Okay, why? You know, so the main idea here, let me actually switch back to color. The main idea is order statistics, right? This counter x that I'm storing in memory, x is the minimum of t. Remember, t is the actual number of distinct elements. T independent uniform random variables. Right, so uniform between 0 and 1. Okay, and what are we storing? Yeah, so we're storing the minimum, okay, right? Because let's say the actual distinct numbers in the stream are, you know, I1, I2 up to IT. So what are we storing in our memory? It's the min of h of I1 up to h of IT, okay? And so what does that look like? Here's 0, here's 1, what do we expect? Okay, so let's just easy one. Let's say we only had one distinct number in this stream. Okay, so X is just storing, H of one, where, one is the only thing that ever appeared in the stream. So if we have a uniform, if we know H of one is uniform between in the interval from 0 to 1. So what do we expect H of 1 to be? Just anyone just unmute yourself and say it. Make sure I'm not talking to myself here.
1/2.
1/2, right? So a uniform random variable, we expect it to be a half. Okay. Now, we don't have one random variable, but we have t, and we're taking the minimum of these t random variables, and they're independent. What do we expect the picture to look like? So we'll prove it, but kind of what the truth is that you expect them to be evenly spaced. So there's something like this. So this one here is going to be roughly 1 over t plus 1, 2 over t plus 1, 3 over t plus 1, and 4 over t plus 1. So here where t is 4. So a fifth, 2/5, 3/5, and 4/5. If you had 5 distinct elements in the stream. So you expect the minimum to be 1 over t plus 1, right? So, and what are we returning? We're returning 1 over x minus 1. So 1 over x is t plus 1. And then you subtract 1, t plus 1 minus 1 is t. Okay? So that's why we're returning what we're returning during a query. Okay. Now, what could go wrong here? Of course, the thing that goes wrong is that this is a random process. X in expectation is 1 over t plus 1, but it's not guaranteed to be 1 over t plus 1. There's going to be some variance. So our response to the query is not necessarily going to be exactly correct, right? We have to show then that it's going to be approximately correct with decent probability. And even that's not going to be true. So we're going to modify the algorithm in a similar way to what we did with Morris, where we kind of beefed up the algorithm to improve its approximation factor and also to reduce its failure probability. So the first claim is that the expectation of x is 1 over t plus 1. And what's the proof of that claim? Well, whenever you have a non-negative random variable, right, its expectation is the integral from 0 to infinity of the probability of a tail bound. Okay. This follows by, for example, integration by parts. I'm not going to show it here. Now we know that our random variable can never be bigger than 1 because all of the hash function can never give you an output that's bigger than 1. So this is the same thing as just integrating from 0 to 1 for us. Okay. This is supposed to be a small x. Okay. So remember now, capital X is the minimum hash value. Okay. And let's say for us now, we're going to say that let's say that the t hash values are, let's call them capital X1 up to capital XT. So if the minimum is bigger than x, that's the same thing as saying that all of them are bigger than x, right? So this is equivalent to saying that we have the event that for all, let's say I, capital Xi is bigger than x dx. Okay. Now, remember that these are independent random variables. So the probability that x1 is bigger than x and x2 is bigger than x and x3 is bigger than x is the same as the product of the probabilities, since they're independent. So this is the same as the product I goes from 1 to t of the probability that xi is bigger than x dx, right? And now what's this picture here? We have 0, 1, we have this interval, and then capital Xi is a random number in this range, and here we have an x somewhere. So here's little x. So we're asking, what's the probability that capital Xi is in this interval. So what is that? What's that probability?
1 minus x.
That's 1 minus x, right? So this is equal to the integral from 0 to 1 of 1 minus x to the tth power dx. Okay. And, you all know calculus. If you do a substitution and integrate this, you will get exactly what I said. You'll get 1 over t plus 1. Okay. So that's that. And remember what, so we got one part of the, picture understood, which is showing that we have some exact expression for the expectation. And now we need to understand how well concentrated it is, which means we need to understand the variance. Okay. And again, remember that whenever you have a random variable, the expectation, right? What is the variance? What does it mean? Variance of a random variable is the same thing as, right, the expectation of that random variable minus its expectation squared, which is the same thing as the expectation of x squared minus the expectation of x squared. Okay. So we know what this is, right? We said that this is now 1 over t plus 1 squared. So the question is what this thing is. And again, that's some computation. And the claim is that the expectation of x squared is equal to 2 over t plus 1, t plus 2. Okay. And the proof is very similar to the last whiteboard in that you integrate. You say the expectation of x squared is equal to the integral 0 to 1, the probability that x squared is bigger than little x dx, which is the same thing. This is the integral from 0 to 1, the probability that capital X is bigger than little root x dx, right? Which is now, I guess, 1 minus root x to the t dx. Okay.
You're missing a square sign on the first line of the proof.
A squared sign?
It should be a probability of x squared is larger than x squared.
Don't I have
so on
that?
the first line of no, like the right-hand side term. Right term. The other term.
The other term? What do you mean the other term?
X squared is larger than x squared, right?
No,
Instead
it's not. This is correct.
Oh,
right?
So you're just
in general, right? Just in general, the expectation of z, any non-negative random variable z, is the integral of probability that z is bigger than little x dx.
all
So,
right. Sorry about that.
So yeah, no problem. So here, my z is just x squared. Okay. And here you can do a u substitution. So, I'll just tell you set u to be 1 minus root x. You do a u substitution, you work this out, you'll get exactly what I told you. I have this computation in the notes, so you can check it for yourself. I don't want to spend time on kind of the little details. So that's it. So we know now that kind of the variance of x, right? We said is the expectation of x squared minus the expectation of x squared. So this is equal to 2 over t plus 1, t plus 2, minus 1 over t plus 1, t plus 1, which I guess is something like, oops, I should turn off my phone. I need to figure out how to prevent my iPad from taking calls too. Anyway, good. So what is this? This is equal to, I guess, 2t plus 1 minus t plus 2 over t plus 1 squared t plus 2, right? And the numerator is 2t plus 2 minus t minus 2. So this numerator here, I can just is equal to actually just t, I think, right? So this is equal to 1 over t plus 1 squared times t over t plus 2, which I'll just note this thing here is less than 1. So this is less than 1 over t plus 1 squared, which is also just the expectation of x squared, right? So we have that the variance in our case is at most the square of the expectation. Okay. Now, right, you want to use Chebyshev's inequality, but you're not going to get something good here because your concentration is, I mean, there's no epsilon here, there's no delta here. So what do you do to ensure that you get 1 plus epsilon approximate error with failure probability at most delta? So we're going to do similarly to what we did last time. We're going to plus the algorithm. What did that mean? So we're going to instantiate R independent copies of the FM algorithm. Let's call them FM1 up to FMR. And then to answer a query, we're going to say, let xi be the output of FMI. Okay. We're going to output x tilde to be equal to 1 over the average of the xi's minus 1. Okay. So the point is, right, normally, what we wanted to be true is that so this thing has the right expectation, right? Each xi has the right expectation. Each xi is 1 over t plus 1. So we said if we invert it and subtract 1, we hope we get the right answer. But there's some variance there. So now what we're doing is we're saying don't just, in the denominator, put something that is not just expected to be 1 over t plus 1, but is has good concentration and is very likely to be very close to 1 over t plus 1. Okay, and we're accomplishing that by averaging. And then now that we have that this thing is concentrated, then we can subtract 1 and get the answer. So the claim is that this works. So the claim we have to set R. So we're going to set R in a moment, not yet. Okay. The claim is that the probability that x tilde, or I shouldn't call this x tilde because it should be called t tilde because it's an estimate of t, not an estimate of x. So let me actually rename it. The probability that t tilde minus t is bigger than epsilon t is going to be at most eta once we appropriately choose R. Okay. So what do we have here? So let's prove this. So what's the probability that this thing here, 1 over R sum of xi, is very far off from what we expect it to be? Right. This is at most the variance, which we know is 1 over t plus 1 squared, over this thing on the right-hand side squared, which is epsilon squared. Oh, okay, so, and the variance decreases by a factor of R, so times 1 over R, right? When you average R independent copies of some random variable, the variance of that average is 1 over R, is an rth fraction of the previous variance of what the variance would be for one copy. That's exactly what we saw before for the Morris plus, when we were talking about Morris last week, Wednesday. So we gain this factor of 1 over R in the numerator. This is the variance in the numerator. And in the denominator, we have the right-hand side squared. So that's epsilon squared over t plus 1 squared. And then stuff cancels, right? T plus 1 squared cancels here. And this is 1 over epsilon squared r, which I can guarantee, I can say this is less than eta if I pick r to be, let's say, 1 over epsilon squared times eta. Okay. Guess the ceiling of that. R has to be an integer. So now back to the claim, we want to understand, what t tilde looks like. So now, if this event happens, namely that average is really close to 1 over t plus 1, then we know that t tilde looks something like 1 over 1 plus or minus epsilon times 1 over t plus 1 minus 1. And this is equal to 1 plus or minus O of epsilon times t plus 1 minus 1. Right? So just, all I'm using here is that basically 1 over 1 plus epsilon is, basically 1 minus O of epsilon. And also 1 over 1 minus epsilon is just 1 plus O of epsilon. Okay. So 1 plus or minus epsilon is in the denominator, but that's similar to being in the numerator. And then I know that this thing here is the same thing as 1 plus or minus O of epsilon times t plus or minus O of epsilon, right? Because there's this 1 here that cancels the 1 here, except that the 1 also gets multiplied by an epsilon as well. So that brings me this extra O of epsilon. But, there are basically two cases. First of all, t has to be a non-negative integer, right? T is the number of distinct elements. So it's either 0 or 1 or 2 or 3. If t is 0, then I claim this is a really, everything works. If t is 0, that means you saw nothing in the stream, which means x is the same as its initial value, which is 1. 1 over 1 minus 1 is 0. So, if you don't see anything in the stream, then you're going to output the right answer. You're going to say it's 0. Okay. Otherwise, t is at least 1. And if t is at least 1, then O of epsilon is also, O of epsilon t. So then this is, 1 plus or minus O of epsilon times t, maybe epsilon being adjusted by a factor of 2 or something. So
Quick question.
Yes.
Is there a parentheses in the middle t plus 1 term? Is there a set of parentheses around that?
Yes.
Thank you.
No problem. Thanks. So, so this analysis did increase epsilon by a constant factor, which depends on kind of these inequalities here, and also the fact that I did this thing over here. You could dig through and kind of be more precise about what the constant factors are, but I promise you, all it means, right, is that you just have to change epsilon. Just run this argument with epsilon smaller by a constant factor, so that call it epsilon prime. So if epsilon prime is at most 3 epsilon, just set, run this algorithm with epsilon prime being epsilon over 3. And then all that will do is change r by a constant factor. So r is going to be, still big O of 1 over epsilon squared eta. Okay. So that's FM plus. Okay. And now there's the usual, FM plus plus, just like with Morris. Right. With Morris, this method of median of means was not optimal, right? I told you there's a better way, but I told you about that method because it's such a generic way of getting better failure probability and getting better approximation ratios. Like, here it is also appearing in the next problem, and it's going to appear kind of all throughout the semester. So I think, from now on, after you've seen the second example with distinct elements, kind of once we have a basic estimator that's gives an unbiased estimate of something interesting and has bounded variance, then I'm just going to assert, therefore, we can do the usual median of means trick and get, blah, blah result. So here I am actually going through the steps again, going through the motions, but, I don't want to, from now on, I'm not going to go through the motions in such detail because it's basically all the same trick over and over again. So what is FM++? We're going to instantiate S copies of FM+, call them FM+1 up to FM+, S. And then when we see something in the stream, we feed that update to all the copies. And then to answer a query, we'll query each FM plus I to get estimates T1 tilde up to TS tilde, right? And then we're going to output the median of them. Oh, and I should say, when we instantiate the S copies of FM plus, we're going to do it with a failure probability of eta again being a third. Okay. And then again, the Chernoff-Hufting bound implies that. Okay, so first of all, what do we know? Right? We know that in expectation, at most a third of the copies, at most S over 3 copies fail to give a good answer, which means that in expectation, at least 2/3 of the copies give a good answer. Okay, so we know that, we expect at least 2 S over 3 of the TI tildes to give a good answer, which means to give a 1 plus epsilon approximation. And the median is good as long as, more than S over 2 of the TI tildes are good. Okay. Right, I mean, I said that last time, but just to make sure that we're all on the same page here, I mean, why is that the case? Basically, imagine that the estimates you're getting are sorted, right? So, you got this estimate, you got this estimate of the number of missing thousands, you got this estimate, these are in sorted order. They're S estimates that you got. The median, of course, is the estimate that's right in the middle in the sorted order. Okay. Now, what does it mean that the median is bad? Well, if it's bad, let's say it's not giving you a 1 plus or minus epsilon approximation, then, I guess you all are seeing all my text and whatnot as well, aren't you? I need to figure out how to disable. There should be, I'll figure this out.
There's a do not disturb that will turn off all your texts.
Oh, really? Okay. See, you can tell I'm not good with technology. So
if you swipe down from the top, if you so the moon icon, if you press the moon icon, okay, now I don't think we'll see your text.
Okay, so how's that? Well, we'll see. We'll see whether this works. Yeah. So good. So right, the median is good if the estimate it's giving us is between 1 minus epsilon times the answer and 1 plus epsilon times the answer. That's what it means to be good. So what does it mean that it's not good? It means that it's either too small or it's too big, right? Now, if it's too small, if the median is too small, then that means that everything less than it also has to be too small, right? So if it's too small, then all of these are too small, which is at least, S over 2. Similarly, if it's too big, then all of these would be too big. which means that you have at least S over 2 that are too big. Okay. So, I mean, that's really, just to be precise, that's why I'm saying as long as the median is good, I mean, as long as, for the median to be a bad estimate, it means that more than half of the TIs have to be bad, right? So, but, we only expect a third of them to be bad. Okay. So, we expect a third to be bad, but actually much more are bad. A half are bad. S over 3 are bad. So kind of the number that we're bad is S over 6 more than what we expected. It's an additive S over 6 more than what we expected. Okay. Or it's a constant factor more than we expected. It's like, yes, we expected S over 3, we got S over 2. So it's kind of 2/3 more than, 60-something% more than what we expected. And the Chernoff-Hufting bound implies that the probability of that happening is at most something that's, exponentially small in S. So as long as we choose S to be, some constant times log of 1 over delta, this is, I guess this doesn't, okay, I don't know. Sorry, this is kind of embarrassing. Let me try to figure out how to, okay. I think there's also a way to just not get text in my, or to go, maybe I should just go into, what's it called?
In settings, you can
Airplane
turn off
mode.
notifications altogether.
I think, that too. And I think
yeah,
you can also just
airplane
go into
mode.
airplane mode and keep the Wi-Fi on, right?
Unless you're coming in through iMessage, in which case I think Phil's still
okay. So then I should go into settings. And where is that? Notifications?
notifications.
And
on messages, it's turned off.
there's that one as well. And then there's
Yeah.
iMessages too. I'll figure that out later. But I think notifications are off. That's good enough, right?
Yeah, it should be.
Okay. Okay, good. So anyway, so overall, our memory then becomes, R times S, real numbers. Remember, what are we storing? We're storing the minimum hash value, which is a real number. Yeah, so, and this R times S is equal to O of 1 over epsilon squared times the logarithm of 1 over delta. Okay. So
I have a question about something
yes,
here.
Yeah.
So with the median, like with like the half the values, the median, and then we have 1/3 that we expect to be bad.
Yeah.
Do we expect the 1/3 that are bad to be distributed on like both sides, like 1/3 less and 1/3, like 1/3 lower than the like 1/3 epsilon on the left side and the right side like bigger and less than the number, and so maybe we could have it even like take less copies than 1/3.
Yeah, I see what you're saying. You're saying that, yes, in the worst case, the ones that are bad in the worst case could all be on one side, but maybe they're kind of, given that they're bad, maybe they're equally likely to be on the left or the right.
Mm-hmm.
So that is true. I don't know. I mean, maybe such an analysis could be pushed to get a better constant factor in your space bound. One thing I will say is that I think there's a bit of an echo, so you might want to.
Oh, sorry.
Someone might need to mute. Yeah. So one thing that I will say is that, when we actually talk about a non-idealized algorithm where we measure things in bits, 1 over epsilon squared times log 1 over delta is actually a lower bound for this problem. It's impossible to do better in bits. So you're not going to, any kind of clever such reasoning is at most going to improve the constant factor. So that is something that I'm sure of. Okay.
That makes sense. Thank you.
No problem. So good. So that's it for the idealized algorithm. Now I want to start making this algorithm not idealized. So let's say removing the idealized assumption. Okay. So there are two algorithms that I'm going to discuss. Both of them are going to be in the notes fully analyzed. In class, I think I'm just going to I'll sketch the first one. I'll try to do a little more than sketch the second one and actually, do some real computations. But again, if you want to see every line of computation, you can look at the notes, which are going to be put online pretty soon. Okay. And I should say the notes for Morris are already online. So there's one PDF on the lecture website, and it's just kind of being written in a chapter every few days. Okay. So chapter 1 or chapter subsection 2.1, which is kind of approximate counting in Morris, is already there. So we want to remove the idealized assumption. So the first algorithm I'll show you is an algorithm called the KMV algorithm. And KMV stands for K minimum value. And this is due to Bar-Yosef, JRAM, Kumar, Shiva Kumar. That was very bad handwriting. And Trevisan back in 2002. And what does the algorithm do? It's as the name suggests. Okay. So we're going to trade off space and variance in a different way. So we're going to see that if you increase the space, you can reduce the variance. I mean, we already saw that with FM plus, but we're going to do it. We're going to use a different approach for this problem, which works as follows. We're going to store not just the minimum hash value, but the k smallest hash values. Okay. So let's say that I'm going to use x to denote the k smallest hash value. And then query, I say, if I've seen less than k distinct values, answer exactly, right? If I've seen less than k distinct values, then, again, in the idealized setting, what's the probability of a hash collision, right? What's the probability that h of 5 equals h of 3? It's 0, because these are, real numbers between 0 and 1. There's 0 probability that I get two uniform real numbers that are exactly the same. Okay, so if I've seen less than k distinct values, I mean, basically I can be sure that I've never seen a repeated, hash value. So it's not the case that I've seen 4 hash values, but actually there are 5 elements I've seen, just 2 of them happen to have the same hash value. That's not going to happen. Okay. Again, so I haven't removed the idealized assumption yet. I will. So if I've seen less than k distinct values, then I'm storing the k smallest hash values I've seen. So that means I'm storing them all. So I know exactly how many distinct values I've seen. I just answer that. Otherwise, I return k over x. And I could put the -1, but it doesn't really matter, because the point is, once x gets big enough that this matters, that means x is at least k. Then you can prove that having the -1 or not is not really going to affect the answer by more than a 1 plus epsilon factor. Okay. Good. So let's now remove the. So first of all, I want to give the intuition for why this works, And then I want to talk about how you can implement this without, without the idealized assumption. So I guess, as I said before, your hash values that you're seeing are in this interval from 0 to 1, and you kind of expect them to be evenly spaced, 1 over t plus 1, 2 over t plus 1, t over t plus 1. So what do you expect the kth smallest to be? You expect the kth smallest to be k over t plus 1. So if you invert it, you hope that x is close to this. So if you invert it and then multiply by k, so k times 1 over x, you hope that this is basically approximately t plus 1. Okay. And again, we know that, we're going to output the answer exactly if t is less than k. So, if t is bigger than k, then the difference between t and t plus 1 is a multiplicatively, at most a 1 over k, 1 plus 1 over k. So notice, notice if t is at least k, then, t plus 1 is at most, well, it's equal to, I guess it's at most 1 plus 1 over k times t. So, as long as 1 over k is like much less than epsilon, then this is not really affecting our kind of multiplicative guarantee anyway. And that's going to be the case. We're going to end up picking k to be like 1 over epsilon squared or something. Okay, so that's why we're answering the queries the way we're answering them. Now, why are we doing this at all? So we're doing this because kind of, we know that the median, intuitively we know like the median is the most kind of robust order statistic, right? In order for the minimum hash value, you have t independent random variables. In order for the minimum to not be what you expect, all you need is kind of one of these t random variables to deviate wildly. And just one of them deviating wildly can affect your minimum, because that thing can be the minimum. For the median to deviate wildly, you basically need like half of your random variables to all deviate wildly, which is very unlikely, right? It's gonna, the probability that it happens kind of decays exponentially with the number of random variables you have. So, the problem is, in order to keep, we would ideally just base our estimate off the median. The problem is, in order for us to know what the median is, we need to store the bottom half of the hash values, which is a lot of memory. The median is the t over 2th order statistic. So we need to keep track of the bottom t over 2 random variables to know what the median is. So the reason we're not using the median is because we can't afford it. So let's just pick something kind of in between. The basic FM was the absolute smallest order statistic, the minimum. The median is the halfway mark. It's the t over 2th. So, there's a trade-off here is what I'm hinting at. There's a trade-off between what order statistic you use and kind of the variance that you're going to get. And the median has the smallest variance, but it's very expensive memory-wise. The minimum has terrible variance, but it's very cheap memory-wise. You just store one value. So we're going to trade off, and we're going to store k things and hope that our variance goes down. And it turns out you can analyze this. The analysis is going to be in the notes. But how do you now implement this without running into the same idealized hash function assumptions? And we're going to implement this via kind of a pseudo-random hash function. And what is pseudo-randomness? This is a field of study. There's a book, you can find a book, for example, by Salil Vadan called Pseudo-Randomness, an entire book on pseudo-randomness. So what is this whole field about? It's about kind of generating many random bits from many fewer, let's say. Many fewer uniformly uniform and independent random bits such that, some algorithm or a class of algorithms, still behaves in a desired way. Okay. So, we could feed the FM algorithm or this KMV algorithm a truly random hash function. Okay, that would be a lot of, uniform random bits. I mean, but that's expensive memory-wise to store such a hash function. So instead, this hash function is going to be implicitly defined, right? These random bits here, when I say generating many random bits from many fewer, of course, these many random bits cannot possibly be independent and uniform because there's just not enough entropy in the system, right? If you're generating n random bits from r random bits, and r is much less than n, well, first of all, your n random bits at most have r bits of entropy. So, they're not going to be independent uniform random bits. Otherwise, they would have n bits of entropy, and they don't. They only have r, right? So they're not perfectly uniformly IID, but the hope is that they're good enough that they still function for your purposes. And I guess one of the classic places you see this happen, pseudo-randomness, is in hash functions for the dictionary problem, right? Hashing with chaining for the dictionary problem. So if you've taken 170, you've seen this. Some of you I know who maybe came from other institutions didn't take 170. Whenever you took your algorithms course, you probably saw in the dictionary problem, right? What is the dictionary problem? It's hash tables. Right. So the idea is I have n items in a universe that comes from 1 up to u, and then I store them in a hash table of size n, which is size m, which is only O of n, and I do it using a hash function which maps the universe into a range, which is the size of the hash table. So basically, I have this hash table. It has size m, and each entry in the hash table is actually a pointer to a linked list. And this is, the set of all keys in my dictionary, such that all keys, let's say I in my dictionary, such that h of I is equal to 1, because this is the first entry in the hash table. And similarly here, this would be all, the set of all keys such that h of I is equal to 2, right? And if you use the perfectly random hash function, it's, you could analyze it and say, an expectation h of I, if you look at the linked list containing h of I for any fixed I, its size is a constant, right? If you pick m to be linear in n. But it turns out you don't actually need a perfectly random hash function to say that. It's enough that your hash function is pseudo-random, and the notion of pseudo-randomness that you use there, and which we're going to use today, is k-wise independence. Okay. So h for us is a set of functions mapping the domain 1 to n into the range, let's say 1 to m. And the definition, we say h is a k-wise independent family if for all x1 not equal to x2 not equal to xk, and for all, and these are between 1 and n, and for all y1 up to yk, which could be equal in 1 to m, the probability that h1 x1 equals y1 and h and hx2 equals y2 and etc. h of xk equals yk is equal to 1 over m to the kth power. And what's the probability over? This is choosing little h uniformly at random from script h. So this is called k-wise independent. So it's saying that as long as you look at only k inputs at a time, then their behavior is as if h were truly, uniformly random function. So an example is, h is the set of all functions mapping the domain 1 to n into the range 1 to m. This is basically k-wise independent for any choice of k. I just want to check with you all, kind of when I'm over my iPad writing, is the mic kind of sensitive enough that the voice quality is still decent?
Yeah.
Okay.
Yeah.
Good. Okay. And so good. So this is one example of a k-wise independent family. Now, remember, this is all about memory for us, right? So what is the memory storage? What is the memory cost to store a function from this set? So, basically to store a little h in this family in memory, we can use log base 2 of the set size bits, right? Because it's just a set, right? So there's the first element in the set, there's the second element in the set, all the way up to the hth element in the set. We can give them each a name from 1 to the size of it, capital H. And then for me to tell you which one you have, it just takes log of the set size bits. Okay. Now, sorry, I just realized. So this is log of the set size. So yeah, not absolute value. So log of the set size bits. Now, what is the set size? How many functions are there mapping 1 to n into 1 to m? Basically, I think it's something like m to the n, right? Okay. So this I guess could be the ceiling. So this implies, something like n log m bits. I mean, something that's definitely easy to see in this case would be something like, n times the ceiling of log m, right? Just because you have h of 1, I write that down. That's ceil of log m bits. I have h of 2, I write that down. That's ceil of log m bits, etc. So n times ceil of log m. Okay. So that's not great. That's a lot. Remember, in our case, the target is real numbers, which, okay, we're going to fix that soon, basically just by rounding to finite precision. But even if you round to finite precision and make log m small, n is there, n is huge, right? So that's a problem. So example 2 is polynomial hashing. And this is due to Carter and Wegman from the 70s. And the idea there is, look, let's say that if m equals n equals q, which is a prime power, then I'm going to let the family of hash functions h be basically the set of all polynomials of degree less than k over the finite field fq. So this is basically, h of x equals a0 plus a1x plus a2x squared plus ... plus a k minus 1 x to the k minus 1, where a0 up to ak minus 1 are in the finite field fq. Okay, and you can prove that this thing is k-wise independent via polynomial interpolation. I'm not going to do that today. But the nice thing about this is that it has a small size. The size of h is what? Well, each of these coefficients has q choices. There are k of them, so it's q to the k. So that implies that log of h is k log q, but q is the same thing as n. So this is an O of k log n bits. And for example, in the dictionary problem, you set, this is like universal hashing basically, right? So if k is 2, then what is a degree at less than 2 polynomial? It's a linear function. It's ax plus b mod p, right? That's maybe something you might be used to seeing from kind of undergrad algorithms. So think of k as a constant, then k log n is just O of log n. So instead of using n memory to store this hash function, you're only using O of log n bits to store this hash function. Okay. So now the claim is, back to the KMV algorithm. What we're going to do is we're going to, pick a hash function g, which maps 1 to n into a range, let's say capital M. And think of capital M as large. Capital M will be like something like n cubed. From a 2-wise independent family. Okay. And then we're just going to define h of I to be g of I over capital M. So it's basically round, it's going to be in the interval from 0 to 1, but it's going to be a multiple of 1 over m. So this is exactly what I said we're going to do. We're getting a random number between 0 and 1, but it's to some finite precision. Specifically, it's going to be a multiple of 1 over capital M. And there are things you need to basically now analyze to make this work. I'm not going to do that right now, but I'll tell you a sketch of what you do to prove that this works, and the full details are in the notes, which are going to be online soon. So the first thing you need to do is you need to make sure to check we want that for all distinct I not equal to j in the stream, h of I is not equal to h of j. Remember, because if you look back at the algorithm for KMV, which is right here, we had this part here, which is if you've seen less than k distinct values, we know the answer exactly. Okay. So now that we're not hashing to reals, we're hashing to these bounded precision things. I mean, there is some chance now that 2 distinct elements in the stream actually have the same hash value. So, maybe we saw 0.05 in the stream twice as a hash value, but those 2.05s weren't coming from the same index. They were actually coming from 2 different indices that happen to have the same hash value, and that might confuse us into thinking we've only seen 1 item when we've actually seen 2. So we want to argue that with good probability, all the hash values we see are distinct, from distinct items. So that's the first thing you do. And I'm not going to do that analysis here, but that's something that follows pretty simply from the two universal, the fact that you're a 2-wise independent hash function. It's related to the birthday paradox, right? So the birthday paradox says, if you see root n random, let's say that you have a range of size m, there are m birthdays in a year. Then once you see root m people, then there's probably 2 that have the same birthday. In other words, there's a hash collision where people are getting, you can imagine each person has a random birthday, a random day for their birthday. So these are hash values. Each person is getting mapped to something in the range, which is a birthday. So what's our range? Our range is n cubed, right? Capital M is n cubed, which says by the birthday paradox, once you have n to the 1.5 distinct elements, then you'll probably get a collision. Are we going to see n to the 1.5 distinct elements? No, because the universe's size is only n. So the max the number of distinct elements could possibly be is n. We're not going to see n to the 1.5. So just like the birthday paradox says that it's very likely that you see a common birthday amongst root n people, kind of a similar computation also shows that once you have much fewer than root m, then you're probably not going to have a birthday collision. So that's kind of what's going on here. That's why we chose capital M to be much bigger than n squared. We chose it to be like n cubed because the square root of that is much bigger than n. N cubed was not really necessary. We could have chosen 100 times n squared. That would have still had the same effect that we want. And we also need to also just analyze. Whoops. Also want to just show correctness, even aside correctness with good probability, even aside from this collision and hash functions. And one way of doing that, if you remember, let's go back to the analysis of the original algorithm, the original FM algorithm. Where was kind of, if you try to repeat this analysis, there's one place that there's a problem, right? And kind of where is that place that there's a problem? Which line is it? Any takers? Any guesses? So yeah, I'll tell you the line. You're going to tell me why this is a problem. This line right here, this equality is a problem. Why is that?
No, they're not t-wise independent, right?
Yeah, exactly. They're not t-wise independent. T could be huge. T could be as big as n, right? This line is saying that what's the problem that all of the xi's are bigger than little x? Well, since they're independent, it's the product of the probabilities. That's not true anymore, right? Because they're not fully independent. They're only 2y's independent. So, what's going to be our way around that? We're just going to analyze it in a slightly different way. We're going to say, look, we're going to say that the new argument is going to be that, we're going to have a problem. We have a problem if k over x is either kind of too big or too small, right? We want this to be bigger than 1 minus epsilon t and less than 1 plus epsilon t. So the only way that's not going to happen is it's, trivially, it's either too big or too small. Now, this is the same thing as saying that, we have a problem if either x is too small or too big, right? If x is too small, then k over x is going to be too big. If x is too big, then k over x is going to be too small. Okay. Now, what does it mean that x is too small? Okay. Remember, x is the kth smallest hash value. So if x is too small, that means we had k. That means that we had k hash values that were too small. That were, let's say, we had k hash values that were too small. I mean, like less than some threshold. What does it mean that x is too big? It means we had less than k hash values that were smaller than some other threshold, right? Meaning that the kth was bigger than that threshold, which was a problem. That meant that the kth was bigger than threshold prime, right? And threshold prime is too big. Okay. And now, so how do you then analyze something like this? So let's look at this case first. So we said k, if x is too small, that means we had k hash values that were too small, less than some threshold. Let's call this threshold alpha. Let's call this threshold prime. Let's call this beta. So define an indicator random variable yi, which is 1 if, let's say first of all that the actual distinct elements in the stream are, let's call them I1 up to, IT. And actually, let's call this Yj. So define Yj to be 1 if h of ij was, what did I say? We have a problem if there are too many guys that are smaller than this threshold alpha. Okay. 1 if, this should be I sub j, if this thing is less than alpha, and 0 otherwise, right? So we have a problem if too many yj's are 1. If in fact if at least k of them are 1, we have a problem, because that means that x is going to be too small. It's going to be at most alpha, and if x is at most alpha, then that means that k over x is going to be too big. It's going to be bigger than 1 plus epsilon times t. And how do you go about this kind of analysis? You say, look, I can define y to be the sum over j from 1 to t of yj. Then the expectation of y is equal to, the sum j goes from 1 to t of the expectation of yj. Okay. Does this computation need independence? No. Linearity of expectation always holds whether or not you have independence. And also the variance of y is equal to the expectation of y squared minus the expectation of y squared. We already know that this doesn't need independence. And this is the expectation, is the sum basically over all j1 and j2 of the expectation of yj1, yj2. This is only looking at 2 variables at a time, right? So this is determined by 2y's independence, right? So in other words, the variance is determined by 2y's independence. Does that make sense? So what you're going to do is you're going to say something like the following. Again, I'm not doing it live because it's in the notes. It's a calculation. You're going to say, look, in order for my estimate to be too big, that can only happen if the kth smallest hash value is too small. But for that to happen, it means I have k random numbers out of these t that are all too small. Okay. And that's unlikely. Why is it unlikely? It's unlikely because I'm going to calculate the expectation here of how many of them are too small. And that's going to be something, if this thing were something like, if this number were much less than k, right? In expectation, I expect way fewer than k to be too small. And I have some decent bound on the variance. Then by Chebyshev's inequality, the probability that I have at least k that are too small is not large. It's unlikely, right? So it's unlikely that x is too small, meaning it's unlikely that our estimator is too big. And I can do the same kind of game in the other direction. I can set up some indicator random variables for h of ij being bigger than beta, where beta is some other threshold. And I can say, look, in expectation, the number of hash values that are bigger than beta is large. It's much bigger than k. So the probability that I have too few people who are bigger than beta, fewer than k that are bigger than beta, that the probability of that happening is very small, again by Chebyshev. Because I expect there to be much bigger than k, many more than k that are bigger than beta. Okay. So that's basically the argument without me actually telling you how to set alpha and beta and actually writing down the calculation, but that's the idea behind everything. So I think we're out of time. There's one more non-idealized algorithm that I'm going to talk to you about on Wednesday before we move into the next topic. But are there questions about, I guess, the again, I didn't show you the full details of this proof, but I showed you the strategy. Are there questions about about the strategy of this proof or anything else? Feel free to unmute yourself.
For k-wise independence, I didn't really understand what the definition was.
Oh, the definition of k-wise independence?
Yeah.
Yeah, so, right, so, okay, so this is, let me give an, let's do a little example then. Maybe I can stop the recording for now and just take questions.